Okay, let's go through the contents of this video. First, I will give introduction to the state space model of the systems. Then I will talk about the solution of homogeneous state equation. Then I will explain the state transition matrix and its basic properties. Then I will take one example of solution of the homogeneous state equation. And then I will give the steps of solution of non-homogeneous state equation. And then I will take the two examples that will show you the solution steps of non-homogeneous state equation. And in the last, I will explain one MATLAB code for solution of the state equations. So let's go ahead. But before going ahead, I recommend you to watch my following video, that is an introduction to the state space analysis, physical systems modeling. This current video is actually based on the theory which is presented in this video. So if you go through this video, you will have the better exposure about the current video. So this video is found on the link that is given in the description. So let's start the topic. So let us consider a multi-input, multi-output system as shown below. So ut is the input and yt is the corresponding output, and xt actually the state variables which are chosen for this system. So here since it is a MIMO system, so ut is not a single input, it is actually there are total r number of inputs from u1 to ur. Similarly, we have the m number of outputs from y1 to ym, and the system is well represented by n number of selected state variables from x1 to xn. So we know that in state space such MIMO systems can be well represented by the following two equations which are known as the state equations. The first equation is the d by dt xt axt plus but, and the second is the yt equal to cxt plus dut. For simplicity, sometimes this t variable is omitted. So in short or in compact form, you can write these equations as x dot equal to ax plus bu and y equal to cx plus du. And now let's go for the solution of the state equation. First, we will consider the homogeneous equation case. So let's consider the MIMO system having the following state equations. So the first one is x dot equal to ax and second one is y equal to cx. So we have just seen in the previous slide that this equation was carrying the u part, I mean the input part plus bu, and this equation was carrying the plus du part. So u is missing here, that means the input is not applied to the system. So we get these reduced equations. So by looking this equation number one, obviously it is the case of the homogeneous matrix differential equation. So in this case, as I said, the input is absent, therefore output yt is only because of the initial conditions present in the system. So if initial conditions are also 0, then definitely output will also be 0. But if the system has some initial conditions, then we have to solve this equation 1 first. So from this equation we will find the value of x. So once this x is known, we can substitute x here in this output equation, so we can find the output yt from the equation 2. So that is a complete solution of the system in the state space when the input is not present. So let's write this equation again. So to have the solution of this equation, we have actually the two approaches. One is the time domain approach and second is the frequency domain approach. Here for simplicity, I am concentrating only on the frequency domain approach, that is based on the Laplace transform. So to solve this differential equation, we can take Laplace transform. So this x dot becomes, I mean that is a d by dt of x in fact. So it becomes s xs minus x0. So x0 actually indicates the initial conditions and equal to a xs. Okay, this x dot actually the t parameter is not shown here in compact form, equal to a xt, right? So t is also there. So this t is now converted into s, right? So the equation 1 is represented in equation 3 in the frequency domain. So now we'll do some basic algebraic operation. So taking this axs to the left and taking this x0 to the right side like this, and then taking xs common, So when you take x as common, we get the Si minus A equal to x0, and then taking this Si minus A matrix to the right side, we get the Si minus A inverse, right? So if I represent this matrix Si minus A inverse by the matrix, let's say phi s, so I can write this xs equal to phi s into x0. I mean, this equation is written like this as equation 4, and if I take the Laplace inverse, so this equation becomes xs becomes xt, phi s becomes phi t, and x0 is x0, which is independent of the t. So we get this equation 5, which in fact is representing the solution of this homogeneous state equation. But here, since x0 are the initial conditions, they are known, but still this phi t is not known. So let's find what is this phi t. So as I said, this phi t is the Laplace inverse of phi s, and phi s is Si minus A inverse. We have just shown in the previous slides. So I can do some operation. So here taking s common, so this becomes because of power minus 1, it becomes 1 upon s, and inside bracket it is I minus A by s. Okay, so by the binomial expansion, I can expand this series, so it becomes Laplace inverse 1 upon s, and this becomes this expansion I plus A upon s plus A square upon s square plus A cube upon s cube, like that. And now taking 1 upon s inside, I get I by s, A upon s square plus A square upon s cube, like that. Okay, so when I take Laplace inverse of this series, I get simply this. So I by s is I, okay, and A upon s square is At, A square upon s cube is A square t square upon factorial 2 plus, and so on. So if you can identify this series, obviously this is the exponential series. So what is the phi t now? So phi t is simply e power At, right? So from this series, you can write phi t equal to e power At. So from equation 5 can be written as xt equal to e power At x0, because we wrote phi t into x0. So in place of phi t, I can write e power At. So this is the solution of homogeneous state equation, and this matrix can be found simply by taking Laplace inverse of this matrix, as I explained. So this phi t is an important matrix, and it is known as the state transition matrix STM. So there are various methods to calculate this phi t, such as the Laplace transform method, which we have just seen, and other one is the time series method, and other is the by using the diagonalizing matrices, such as the model matrix, which is made with the eigenvectors of the matrix A, and the Vandermonde matrix. So, sometimes it is represented by V or P. This is made with the eigenvalues of the matrix A, and the Jordan matrix, this is also made with the eigenvalues. The Vandermonde matrix uses eigenvalues when the eigenvalues are distinct, and the Jordan matrix uses eigenvalues when the eigenvalues are multiple. So other one is a Sylvester's interpolation methods. So these are some common methods which are used to find this phi t for a system, a state space system. But here in this video, I'm not going to explain all these methods because it will take too much time. So I will try to explain these methods in some other video tutorial. So here I'm concentrating only on the Laplace transform method, which is easiest one. Although this method is the fastest. I mean by using the diagonalizing matrix, because here this is a time domain approach. We do not go for any Laplace. Because in Laplace you have to take the inverse, you have to do the partial fractions, etc. But this is a simple one. It is based on only the matrix multiplications. So this method is faster as compared to the Laplace, but Laplace one is the easiest. So now let's go through some basic properties of this state transition matrix. They are very easy to understand. Anyone can verify them because all are based on the exponentials, right? So for example, phi t1 plus t2 You can write e power a t1 plus t2, and you can separate them e power a t1, e power a t2, and e power a t1 can be written as phi t1, e power at can be written, t2 can be written as a phi t2, like that. So they are very easy to understand. Now let's go ahead. So now now let me explain one example of the solution of the homogeneous state equation using the Laplace transform method. So here is my system. So this is my matrix A. So this is the equation x dot equal to ax, and this is my output equation y equal to cx. So this is my C matrix, this is my A matrix, C matrix. B and D matrix are not there. B is not there because the input is not applied, because I am considering the case of the homogeneous state equation, right? But initial conditions are given, because if initial conditions are there, then only you can achieve some output. If initial conditions are also 0, then there is no need of solution. You will get the 0 output. So let's see how I can find the output of the system y because of these initial conditions. So first I have to find the state transition matrix phi t using Laplace transform method. So as I know, the phi t is the Laplace inverse of Si minus A. So I am doing same here. So Laplace inverse of Si. Si is this matrix. I mean S multiplied with the identity matrix 1 0 0 1. Okay, so it is S 0 0 S minus this is your A matrix. Okay, and inverse of whole. So this becomes S minus 0 is S, 0 minus 1 is minus 1, 0 minus 2, 0 minus minus 2 is plus 2, and S minus minus 3 is S plus 3. So you get this matrix. Now you have to find the inverse of this matrix. So since it is a 2 by 2 matrix, so inverse is easy. You have to simply exchange this diagonal, and you have to change the sign of this diagonal, right, and divide it by the determinant. So it is easy. So S plus 3 and S are exchanged with each other, and minus 1 is converted to 1 and 2 is converted into minus 2 and divided by the determinant. So that is S into S plus 3 minus minus 2, that is plus 2. So that is your determinant. But here remember, to make the further effort simple, you have to represent this determinant in terms of the factors. So that will make your further exercise easy. So like that. So this is actually the S square plus 3S plus 2. So that can be written as S plus 1, S plus 2 in terms of factor. So now you divide all the 4 elements by these two factors, S plus 1 and S plus 2. So that you will get like this. So that is okay, so that is S plus 3 upon these two factors, S plus 3 upon S plus 1, S plus 2, 1 upon S plus 1, S plus 2, minus 2 upon S plus 1, S plus 2, and S upon S plus 1, S plus 2. Now I have to find the Laplace inverse. So to find the Laplace inverse, obviously I have to represent all these 4 quantities or expressions in partial fraction. So I have to do the partial fractions like this. So once partial fraction is done, it is very easy to get the Laplace inverse. So what is 2 upon S plus 1? Obviously it is 2 into e power minus t, and this is 1 upon S plus 2, that is e power minus 2t. So you can write the state transition matrix like this. Okay, so this first one is giving this, second one is the e power minus t minus e power minus 2t, like that. So this is how very easily you can find the state transition matrix with help of the Laplace transform. Although this is very straightforward, very simple, but sometimes it takes time, because you have to do the partial fractions. Although it is a 2 by 2, so no problem. When you go for the 3 by 3 and more dimensions, obviously your exercise will be huge. So in spite of simple, generally we avoid it for the faster operation. So as we know now, since phi t is known, and we know that xt equal to phi t into x0. So now we will multiply this matrix with the initial conditions. So from this you can find the xt. So let's see how. Okay, so this is my phi t, and these are the initial conditions which were given in the question. So when I multiply these two matrices, I get this. So that is your xt. So once now xt is known, you can substitute xt in that output equation y equal to cxt. So you can find the output y. So y equal to c matrix is 1 0 and xt is substituted here. So obviously it is simple multiplication of these two matrices. So you will get only the first term because 1 is multiplied with this and 0 will be multiplied with this. So you will get the first term only. So this is the output of your system, which is represented in the state space because of the initial conditions only. Mind this, here no input is applied to the system. This output yt is because of only the initial conditions, right? Now we will go for the non-homogeneous equations. That means in the previous case we have considered no input, but in this case we will consider the input as well as the initial conditions. I mean, the system has some initial conditions and some input is also applied to the system. Then in that case, how we can find the system response? So here now a system is represented by these two complete equations. I mean, you can see that these u part. So u is actually the input. So you are getting the B matrix and the D matrix also in this case. So again, the procedure is simple. First you have to solve this equation 1. So when you solve this equation 1, you will get the value of x. Once x is known, we will substitute here in second equation, then we will get the equation, output equation y, right? So let's see how we can solve this equation 1, which is the non-homogeneous in this case. So again, I will go through the Laplace transform, I mean the frequency domain approach to solve this differential equation. So taking Laplace transform of this equation 1, so x dot becomes sxs minus x0, axt is axs and but is bus. Okay, it's a simple. And now taking x0 to the right, axs to the left. So you get this. So now taking xs common, we get matrix Si minus A, and then taking this matrix to the right side, I will get inverse of this matrix, and that will be multiplied to these two terms. So Si minus A inverse into x0 plus Si minus A inverse into bus. And what is this Si minus A inverse? In the previous slide, I represented this with phi s. Okay, so I can write this xs as phi s into x0 plus phi s into bus. So this is a very important equation. Memorize it, because I am going to use this equation in solving the various examples. Right, so let me rewrite this equation. Okay, so this is important one, so that's why I am highlighting it. And now taking Laplace inverse of this equation, what I will achieve? So xs becomes xt, phi s becomes phi t, x0 is x0, which is t independent. These are initial conditions. Now what will be the Laplace inverse of this second term? Here two expressions of s are multiplied with each other. I mean the phi s and the us are multiplied with each other, and we know by the Laplace properties, I mean by the convolution theorem, that multiplication in the frequency domain becomes the convolution in the time domain, right? In the time domain. So when you take the Laplace inverse, obviously there will be the convolution between the phi t and ut. So here you can see that this convolution expression is written. You know, this is the convolution, integral 0 to t phi t minus tau b u tau d tau. So that is a simple convolution integral. Okay, and we know that phi t is the e power at, which we have already derived. So this is the complete output expression of the, or you can say that is a solution of the equation 1. That was your non-homogeneous matrix differential equation. So by this way you can get the value of xt. So once xt is known, you can substitute this xt into the y equation and you will get the corresponding output. So now with this theory, let me take one example. So I can apply this theory to solve that particular problem. So here is my system. So one system is described in the state space by following two equations. So that is your x dot equal to ax plus bu. So that is your A matrix, this is B matrix, this is C matrix, D is not present here. and the initial conditions are 0. I'm taking 0 initial conditions. You can take non-zero conditions also, doesn't matter. It will increase your calculation, but nothing else. So what I need to do now, I have to solve this first equation, okay, that is x dot equal to ax plus bu. So when I solve this, I will get the value of x from it. So how to solve it? Again, I will go through this equation. That's why I said memorize this equation, because it is important. And now what I'm asked to do, find the step response of this system. Step response means this input. This input is the unit step, okay. This is the unit step, which is represented by the ut. See, this u and this ut are different representation. Don't confuse that this u is always the unit step. No, this is the symbol u, okay. That's why they are different with each other. The u can be any time domain function. It can be like t, it can be ut, it can be e power minus t, anything. This input can be any input function, right? So here in this case, this is the unit step, because I need to find the step response of the system. So now consider this equation 3, which we have already derived. So in this equation, if you can see carefully, the x0 is known, I mean the initial conditions. Matrix B is known, so that is matrix B. Now US. So what is the US? US is actually the Laplace transform of input, and my input is the ut, that is a unit step. So what is the Laplace transform of it? That is a 1 upon s. So your US is actually the 1 upon s, okay. So now x0 is known, B is already known, US is known, only the phi s is need to be found. Okay, so let me find the phi s, and phi s is very easy to find, because we already know that phi s is si minus a inverse. So I can find easily, and this is already done in the previous example also. So si minus a and the inverse of it. So simply exchanging these two elements in this diagonal and changing sign of these two elements and divided by the determinant, okay. So that is your phi s, and considering the factor of this determinant, so that is s plus 1, s plus 2. It is same actually, because the matrix A is same in the previous example, so the procedure is same. So this is your phi s. So all the 4 elements are divided by these two factors, s plus 1 and s plus 2, like this. So this is your matrix phi s. So phi s is also known. It is very easy to find, just you can see. So now in that equation 3, I know all the matrices. So phi s is known, x0 was given, phi s is known, b was given, and us was the Laplace transform of input. So just substitute all the matrices in this equation. That's it. So phi s, so this is your phi s, initial conditions plus phi s, b matrix, and then us, that was the 1 upon s, right? And here you can see that this matrix is completely 0. So the multiplication of these two is 0. So the first part is eliminated, only the second part is remaining. So you just multiply these two matrices first. So this is 0, and in place of 1 you can write 1 upon s, like this, okay. So now you need to multiply these two matrices. So when you multiply these two matrices, you will get this answer, very easy, because the first element is 0. So the first column will be eliminated, only the second column will be preserved, like this, right? And here you can see that s is also cancelled by the s. So you get this answer, 1 upon s plus 1, s plus 2, and 1 upon s plus 1, s plus 2, right? So that is your excess. And since it is a 2 variable system, so you can represent as x1 s or x2 s. So now I will use these 2 state variables in a frequency domain, and they will be put into the output equation of y to get the output y, right? So this was the output equation that was given in the question. So yt equal to 1, 0, x1 and x2. So in Laplace domain, you can write the same equation like this. So yt means ys, 1, 0, and x1t, x2t means x1s and x2s, right? And now you can substitute the values of this x1s and x2s, which we have just found in the previous slide. So okay, so this is what I achieve. So ys equal to matrix C, x1s and x2s. So you need to multiply these two matrices. So the one will be multiplied with the upper expression, 0 will be multiplied with the lower expression. So only the upper one is extracted as. So this is the ys. Okay, now to represent this in the time domain, you need to take the Laplace inverse. So first represent this in the partial fractions and take Laplace inverse. So this is the Laplace inverse. I mean, this is the yt. So what is the yt? Yt is the output of your system. So if you apply the unit step to this system, you will get this type of output. Okay. So this is how you can solve your state equation for a particular input. Now let me take one more example, which is slightly complex than the previous one. Here I am taking a 2 input 2 output system. So here I have the two inputs u1 and u2. So these two inputs are, one is the unit step and second is the e power minus 3t ut. So these are two inputs and I need to find the corresponding two outputs y1 and y2. Okay, so this is my A matrix, this is my B matrix and this is my C matrix, and these are the initial conditions which are 0, right? So again, how to find the response, I mean the yt or y1 and y2 for this system for the following inputs. Again, I need to use that equation 3. That's why I said this equation is very important, so you have to memorize. So because for every question you have to use this equation. So now in this equation, let's see what matrices actually are known at this moment. So x0 is given, okay, B matrix is given, B is already given, and US, what is the US? US is the Laplace transform of this input matrix, right? And so obviously, just like the previous example, only the phi s need to be found. So once phi s is known, we can substitute all the matrices here. And once xs is known, we can substitute xs here and we can find the output y, just similar to the previous example. So now let's find the US. So as I said, US is the Laplace transform of these two inputs. It's a column matrix, remember. So ut is 1 upon s, that is a unit step, and then e power minus 3t is 1 upon s plus 3. So this is your US. So in this equation, x0 is known, b is known, US is known, only phi s is remaining. And phi s is actually is the same which we have obtained in the previous example, because the A matrix is same in both the example. That was 0, 1, minus 2, minus 3. So since A matrix is same, again we will get the same phi s. So we can try again. So this is the phi s which we have already obtained in the previous example. So now in the equation 3, all the matrices are known, so I can substitute all the matrices like this. So this is the phi s, initial condition x0, plus phi s, b and us, right? Because of this 0 matrix, the first part vanishes, only the second part is remaining. So first we will multiply these two matrices. So when you multiply these two matrices, let me rewrite again. Okay, so you first multiply these two matrices, you get this. Okay, very easy. And now you multiply these two matrices again, so you will get xs. So this is how you achieve these two values in this matrix. So that is your x1s and x2s, right? Here I recommend you to find the Laplace inverse of this x1s and x2s. So you can represent them in time domain, right, like this. So you just take Laplace inverse, ILT. So let me take how I can take Laplace inverse. For Laplace inverse, obviously you need to express these terms into their corresponding partial fractions. So that is easy, but obviously it is a time taking. So I can take Laplace inverse, so I can find x1t and x2t in the time domain. So the first term gives the Laplace inverse. So this is the expression. This you can achieve by taking the partial fractions, and the second term will give this Laplace inverse, right? So now x1t and x2t are known, so I can substitute x1t, x2t in the equation of the y. So y is equation that is given in the question. So y, which is in fact the two outputs y1 and y2. So this is your C matrix. So y equal to Cx. Okay. So here in this place x1 and x2, you can substitute this matrix, right? So I have done this substitution. So this is your C matrix, and this is your x1 x2 matrix. So you just need to multiply these two matrices, you will get this answer. So obviously the first row is your y1 and second row is your y2. So you achieve the two outputs of the system like this. Okay. So y1t is this expression and y2t is this expression. So this is how you could solve a complex state space model, and you could find its response to the corresponding two inputs, I mean the ut and e power minus 3 ut. So the procedure is simple, right? But it requires efforts, no doubt. So to reduce that effort, I have written this MATLAB code. So this is a very capable and efficient MATLAB code which can solve any state equation. Okay, whether it is a homogeneous or non-homogeneous case, you just give the inputs such as the matrix A, B, C, D, initial conditions and the input, that's it. You give all these input to this program, it will solve the corresponding state equation for you and you will get the answer. So it's a very powerful tool which I have developed, and you can utilize this tool to cross verify your various problems of your textbook. Okay, and let's understand this program. So with these commands, I'm getting input from the user at the command prompt. So user will enter the matrix A, B, C, D and the initial conditions, and user will enter the input, but this will be in the text string form. So if input is ut, the user will enter ut like this. Okay, and if input is let's say e power minus 3t, the user will enter this as exp minus 3t. Okay, so in this single quotes means it's a string, character string. So when I will run this program, I will also show you that how you can enter these inputs. So this command will convert the text string into the symbolic expression. Let me also tell you, I am using the symbolic maths toolbox, and I'm using the 2018A version of MATLAB for my case. Okay, and here I have actually created one function that is a SS solve. That means state space solve. This function is receiving all these matrices A, B, C, D, initial conditions and the input functions, and it solves the state equation, and it gives the three outputs. The one is the y, that is the output expression, xt, that is your solution of state equation, first is state equation, I mean x dot equal to ax plus bu, and phi t. Phi t means that is a state transition matrix. So you get the three outputs by this function. Okay, and here I am just displaying the phi t and xt and output y. Okay, and I am also plotting the input and output. So let me show you what I have written inside this function SS solve. Okay, and how it is solving the state equations. And also I recommend you to use the live editor in the MATLAB to run this program. Although you can use the normal editor, but the output which you will obtain in the normal editor are not easily readable. Okay, they are not in the standard formats. They are in a MATLAB format, default formats. For example, e power minus t is not written as e power minus t. In MATLAB, it is written as exp minus t. Okay, but if you use the live editor, you will get the expressions in this form. So you will get the better formatted outputs in live editors. Okay, so now let me show you the code of this function sssolve. Here the symbolic variable as is declared, then size of matrix A is found, and then identity matrix of that size is created, and then I find the Laplace transform of input. Okay, so this becomes US. So sorry, UT is converted into US, and now with this line phi s is found, phi s. So phi s is Si minus A inverse, if you remember, Si minus A inverse. So I am getting inverse of this matrix, and then this is xs. So this is your equation 3 which we have used in all questions. So that was phi s into x0 plus phi s into b into US. So that equation 3 is written here, and then taking inverse Laplace of this phi s, you will get the phi t. So you will get phi t here, and then taking Laplace inverse of xs in this code, I Laplace xs, you are getting xt by this code, and this is the Laplace transform of your output equation. So this is your actually ys equal to cxs plus d us. So this is how this equation is written here, and taking inverse Laplace of ys, you are getting the yt. So this is a very simple code in fact, and but it is very capable and accurate. So you can solve any state equation with this code. So let me show you how this program can run. So let me take you to the MATLAB, and this is the MATLAB live editor. Okay, what is the difference? Actually the same program is this in the normal editor window. So you can write this program either in the normal window or directly in the this live editor. So live editor you can easily open. If you go to the new, in the new you can click this live script. So when you click this live script, you get this interface where you can write your program. Okay, so here you can see that the screen is divided into the two parts, the left section and the right section. In the left your code is there, and in the right side when you run this program, your all the outputs will be displayed in the right section. Okay, so I have simply copied this code here. So let me run this. So when I run this, the control returns to the command window, and it asks me to enter the matrix A. But before entering the matrix A, let me show you which problem I am solving. So come back to the presentation. So this is example 1 which I have explained and solved all the steps in my previous slides. So I am just rewriting the problem and corresponding solution. So this is my matrix A, this is my matrix C, and the initial conditions are given. Matrix B is 0 because it's a homogeneous case because there is no input. So B is 0, and D is also not in the system, input is 0. So these three matrices are 0. So output Y will be because of the initial conditions only, and as a solution you will get the following state transition matrix phi t and the corresponding output. So let me try that program, and let me enter the matrix A. So matrix A is 0, 1, minus 2, minus 3, right? And matrix B is 0, so 0 semicolon 0. Matrix B is actually your column matrix, and matrix C is there, that is 1 0, right, and matrix D is 0 already, 0, and now write the initial conditions. So 1 semicolon 0. So initial conditions are already given in the question, and now enter the input ut as a text string. The input is not there because it's a case of it's a case of the homogeneous state equation. So you will enter 0 input like this. So press enter. So simulation will take place, and okay, and simulation is done. So you can see that all these variables are created in the workspace. So now let me return to the live script or live editor. So here you can see at the right side you get all the outputs. So you can see that this is your state transition matrix, okay, and this is the xt solution of your homogeneous state equation, these two state variables x1 and x2, and this is your output 2 e power minus t minus e power minus 2t. So you can verify this output with the what we have achieved here, 2 e power minus t e power minus 2t. So my program gave the correct output, and here I have plotted the input outputs also. So this is your input, so which is a 0 line because input is not present, it's a 0, and this is the output. So this equation y is plotted here. So this is how you can solve any homogeneous case like this. So now come back to the another example of non-homogeneous case. Okay, so let's take a second example. So this is the non-homogeneous case. Here x dot equal to ax plus bu. So you have the A matrix, B matrix, you have the C matrix, D is not present here, and the initial conditions are 0. So now you need to find the step response. Okay, step response, your input u is unit step. So you will give input like this in form of string, and this is the output. So you will get the phi t. It's the same phi t because matrix A is same as in the previous case, and this is the corresponding output y t. So let us verify whether we will achieve it or not using that program. So this is my live editor, run this program. Okay, so it asks me to enter the matrix A. So matrix A is same, so I can enter that same matrix. Matrix B is now present, and it is 0 and 1, 0 and 1. And matrix C, it is 1, 0. Matrix D is not there. And now you have to enter the initial conditions. Initial conditions are 0 now. So 0, 0. Mind this, it is a column matrix. And now I have to enter the input. Since I have to find the unit step response, so I have to write unit step like this. Okay, in the quotes, in the bracket 1. So press enter, execution will start, and it is done. So let me return to the live editor. Okay, and this is the output that is displayed in the right section. You can see, so you are getting the same state transition matrix again because A matrix is same, and this is the xt. You are getting the solution of state equation. So the first variable x1 and x2 second state variable, and this is the expression of output yt. So this is e power minus 2t upon 2 minus e power minus t plus 1 by 2. So just verify this with theoretical output. So you are getting the same here, right? So this my program gave the correct output again, and the input outputs are plotted again. So input is the line at 1 because it's a unit step, and the output is this expression y. So you are getting that your output is increasing with time. So this is how you could solve your state equation, that is a non-homogeneous state equation for the unit step input. So now come back to the presentation, and let me try one more example, the complex one. So this is the third problem where this is the A matrix, this is the B matrix, C matrix, initial conditions, and the input. So all the theoretical steps I have already shown you in the previous slides, right? So this is a 2 input 2 output systems. and as a solution you will get the same phi t because the A matrix is same. And as outputs you got these two expressions y1 and y2. So these are the two outputs. So let me try this in that MATLAB program. So run this and then matrix A. So matrix A is again same in this case. So this is matrix A 0 1 minus 2 minus 3, and now matrix B is 2 by 2 matrix. So the first row is 2 1 and the second row is 0 1. Okay, and the matrix C is also a 2 by 2 matrix, and the first row is 1 0 and the second row is 1 1. Second row is 1 1. So that is matrix C. And now matrix D is 0 in this case, also matrix D, and the initial conditions are also 0. So that is a column matrix 0 0 0 0. And now I have to give the inputs as a string. So here I have to give the two inputs, right? So the first input is 1, and mind this, it is also a column matrix, so semicolon, and the second input is e power minus 3t, right, bracket closed and single quote. So this is how you can give these two inputs in form of a column matrix. So by this way you can give any number of inputs and you can write any expression of t. So this program is versatile, right? So it can handle any number of inputs and their corresponding any expression of t. So let me press enter. So simulation is started and it is done. So you got all these variables and workspace. So let me return to the live editor, and in the right side you can see all the corresponding outputs. So this is your state transition matrix. Again, it's the same because of the matrix A is same with the previous example. And yes, this is the solution of the state equation. So xt, this one, these two, and the corresponding two outputs, the first one y1t and y2t. So compare this with my theoretical output. So you can consider y1t, that is 3 minus 2.5 e power minus t minus e power minus 2t plus 0.5 e power minus 3t, and this one. So compare this with here. So again you can see this minus 5 by 2, that is 2.5. So 3 minus 2.5 e power minus t minus e power minus 2t plus 0.5 e power minus 3t. So same expression of y1 I am achieving here, and the same expression of y2 I am achieving here, that is 1 plus e power minus 2t minus 2 e power minus 3t. So the results are verified with the theoretical outcomes, and here are the plots of inputs and outputs. So in inputs, two inputs you can see, one blue line at 1, that is the unit step, and this red, that is the e power minus 3t, and you are getting these two outputs y1 and y2. Okay, so this is how my program could solve all the state equations, whether it's a homogeneous or non-homogeneous equations, whether the input is 0, unit step, or the combination of the two inputs, or you can give any types of input in this MATLAB program. So it's a very efficient and very capable program, so that can solve any question of your textbook. Okay, so you can use this as a tool to cross verify for your theoretical outcomes. So that's it for this video. I hope you have liked it, and I thank you all very much for sparing your time to watch this video. Thank you.